Any idea? Because as I told you, it's carrying negative charge. That means lone pair of electron or two electron is there. Negative charge means two electron. That means it is a electron rich species which can donate a pair of electron to form a new bond. So this is a nucleophile. It will attack from here. Sorry. Yeah. And this bromide will knock out. So why I am showing this way bromide? Because the when this bond breaking will takes place, the two electron will be abstract by bromine atom, because bromine is more electron negative compared to the carbon one. So bromine is halogen and it's more electronegative negative atom. So it will pull the pair of electron to give the Br minus. Br minus. And you will get methanol here. Methanol. So now you can see here, you can compare the charge also. Here one negative charge is there. In product also we have one negative charge. And all the atoms are same as shown in the starting material or a reactant. So this type of reaction is called SN2 because bond breaking and bond making is taking simultaneously. Attack and bond, this bond is breaking simultaneously. So I hope these examples are clear to you. Now we have some examples for resonance structure. In previous slide, I have discussed what is resonance structure. So movement of pi bond or a lone pair of electron is called as a resonance effect. You have seen here, right? Here I have discussed this resonance effect. So just you have to move the pair of electron or pi and pi bond to get the correct resonance structure. So the question is which resonance form contributes the most to the resonance hybrid of this molecule. So if you will see this molecule, which one is electron rich atom? In this molecule you have to find out the electron rich atom. Anyone? Always remember that when any molecule contains heteroatom, then heteroatom like nitrogen and oxygen carries lone pair of electron, and lone pair of electron are always shared by those atom to form the resonance structure if pi and alternate pi bond is possible. Now here you can see we have two heteroatom. One is oxygen, one is nitrogen. Oxygen also have lone pair of electron. Nitrogen also have lone pair of electron. But if oxygen will share lone pair of electron, who will take that electron? Here carbon is already satisfying its valency. That means it is a quaternary carbon atom. Correct? It's a quaternary carbon. So if oxygen cannot share lone pair to form here bond. But here if we will talk about the nitrogen, nitrogen have lone pair of electron, and here we have pi bond also. So this lone pair will be shared by oxygen like this way. This way. You have to show arrow this way. And this the bond will shift this way. Arrow pushing. Then this will go like this way. So what will be the structure? Can match with any structure. Here you can see in A, when nitrogen is sharing its lone pair, it will become positive charge. Correct? It doesn't mean it's the electropositive or electrophile. Electron deficient species is also carrying plus charge, but in nitrogen case, it's because of 4 valency. So it will share pair of electron. Here double bond will come. Then this double bond will move towards here this carbon atom, and here double bond will form. Then because here double bond will form, this bond breaking will takes place, and because electron is more electronegative, the negative charge will come on oxygen atom to get the this intermediate. So the correct answer is A, because here it's satisfying the all valency and charges here. So this is the correct resonance structure. Correct resonance structure. We will check why others are not correct resonance structure. So when lone pair of nitrogen is shared here, the new bond for the pi bond is forming here. Bond formation is taking place, followed by this pi bond breaking of this pi bond. So when this pi bond will break, so the other possible chance is there, negative charge will come over here and rest of the species will remain same. That means the other possible resonance structure is double bond oxygen, sorry, but I hope you are understanding. Positive charge, double bond, negative charge, correct. This is the correct resonance structure. But in case of B, here they have shown the this two pair of electron also along with negative charge. That means this is the incorrect resonance structure. The correct one is this one. And the third possibility, uh, sorry, here third option is C. Here they have shown the oxygen and carbon bond breaking. So if we will see here in first structure we have two pi bonds. One between the carbon oxygen and one another is between carbon carbon bond. But in resonance structure the pi bond count should be remain same. Here we have two pi bonds. Here also we have two pi bonds. 1, 2. In this structure also we have two pi bonds, 1 and 2. So these are resonance structure, but here it is not satisfying the rule. That means this is also ruled out. This is also incorrect. And the another example, option D, fourth option is also incorrect, because again the pi bond is only one here and here we have two pi bonds, and it is not possible to move the electron easily in both the structures C and D. The pi bond or lone pair of electrons should be easily delocalized in throughout the structure, but here it is not possible. So that's why this structure is also incorrect. Now the next example, which resonance form contributes the most to the resonance hybrid of this moiety? So which one is the correct answer? Again you have to follow the same rule. Which heteroatoms we have in this structure? How many heteroatoms? Apart from carbon and hydrogen, all other atoms are called as heteroatoms. So here we have carbon, carbon, hydrogen, and heteroatom is nitrogen and sulfur. Correct? Now, because sulfur have two lone pair of electron and it's sharing two bond with this carbon atom. So this is quaternary carbon, and sulfur cannot form any other bond with this carbon. So this will not share the lone pair of electron. While talking about the nitrogen, it has one lone pair of electron and it cannot share its lone pair towards this carbon atom, but towards this carbon atom it can donate. Correct? Sorry, this lone pair is present here, so it can donate its lone pair. So valency is also important, and electronegativity is also important. The most electronegative atom is nitrogen only, and when it will share the electron pair of electron towards this direction, because why it cannot donate here, because it required next pi bond. Here no pi bond is present, all are hydrogens. Pi bond is not present, that means it is not possible to move share these two pair of electron to form a new pi bond. It is not possible. That's why it will share its pair of electron to form a new pi bond, and here positive charge will come on this nitrogen atom. This nitrogen atom. Then because carbon have only 4 valency, so this carbon sulfur bond will break here. If triple bond will become here with lone pair of nitrogen, then this bond breaking will take place, and because sulfur is more electronegative compared to the carbon atom, it will carry a negative charge. It will pull the pair of electron to give the resonance structure. So which one is similar to this structure? Which option? Option A. So option A is a resonance structure of this model. Correct? Why B, C, D is not? Because here you can see carbon is carrying plus charge. That means it is a electron deficient species. And from starting molecule, we will see here that here no atom is electron deficient. All atoms are equally completing their octet. That's why this is not the correct option. Carbon is not following the octet rule. It has only 6 electrons. Correct. Now the C option also is not satisfying the octet rule of carbon, as well as here also it is not possible. Yeah, here you can see the nitrogen is carrying minus charge while it can form bond here. So this is also not the correct resonance structure, because here only bond breaking is taking place. If you will compare through the this structure, only carbon nitrogen pi bond breaking is taking place. That means it is also not a correct resonance structure. Pi bond should be equal in both the structure. Here we have two pi bonds, here we have only one, so this is also not correct option. And the fourth one also have only one pi bond, so this is also not the correct option. Okay. So I hope all of you are clear in this example also. Yeah. So these are some problems. Draw a single reasonable resonance structure of this species. Use curved arrow. Show lone pair and formal charges. So here we have carbocation here and we have double bonds. So this double bond can delocalize, or you can write resonance structure of this species. Yeah, sorry. This double bond can delocalize here, and if this double bond will form bond here, positive charge will move here. Why? Because if this pi bond breaking will takes place, so one will become electron deficient carbon, one will become electron rich, because this is a polar mechanism, polar reaction. So when, because here we have electron deficient carbon, carbocation, so carbon anion will generate over here and carbocation will generate over here, and this carbon anion will form bond with this carbocation. So bond formation will take place here to give the positive charge at the terminal. You can see here. Correct. This is the delocalization and arrow pushing, and this is your final product. All of you got it? Now this is another example. Here how you can move this positive charge carbocation. Again you have to find out the adjacent double bond. So with respect to this carbocation, you can see the next carbon have this double bond. So this is the possibility where it can shift, it can move. Always remember, if you are moving any charge, positive or negative, the alternate carbon, the next carbon should always carry the pi bond. Then only you can move the charges. So here you can see, you can move double bond here and positive charge will come on this carbon atom. Similar way, the another possibility is there. Sorry. What is the another possibility? You can further move this positive charge. Yes, you can. So here we have double bond, here we have positive charge. So this positive charge, this double bond will move here and positive charge will generate over here. Here, this is the another resonance structure. So remember one thing, I am moving positive charge, but I will not write the arrow from the positive charge. I cannot write this way. Cannot write. This is the incorrect. Completely incorrect. Why? Because it's a electron deficient carbon. Electron deficient all species is there. So the delocalization or movement of electron will always occur from the electron rich species, because double bond have electron rich, means here we have pi bond, so it can share the electron. That's why the arrow pushing is always shown like this only. Here also we are not moving positive charge, we are moving the pi bonds, and carbocation is generated on other end, followed by the delocalization of pi bond. So here also pi bond is delocalizing, that's why positive charge is created on this carbon. That doesn't mean positive charge is moving and you cannot show arrow from the positive charge. You have to show arrow always from the electron rich atom or molecule or species, anything. Okay, all of you are clear here? Now the next point in polar reaction is hyperconjugation. So hyperconjugation is refers to the delocalization of electrons with the participation of bond of primarily sigma character. Yeah. So what does it mean? In same like resonance structure, in hyperconjugation we are moving the bond. We can say the movement of bond is taking place, but the difference is here that there we are moving the electron between the pi bond. Here it is done between the sigma bond, sigma character. So here you can see this hydrogen is breaking bond between the carbon hydrogen, and here we are getting the double bond. Here you can see double bond is forming here, and we are getting this species. So you have to maintain the charge. So you can see here we have one negative charge, one positive charge. Same here, uh, that means it become neutral, and our starting point molecule is also neutral. So the charge should be always maintained after the arrow and before the arrow also. If it will take this proton, it will become this way, correct? Charge will go from here. This will not. So these two are hyperconjugation structures. So this is called the hyperconjugation. Again, if you will move here, you can see again. Sorry, these two structures are same, but apart from breaking this bond, you can break this bond also. So this is also possibility, and the third possibility is also there here. So this pi bond is coming here, moving here, but because pi bond is not moving, when bond breaking is taking place, this carbon carries negative charge, because carbon is more electronegative compared to proton. That's why it will pull the pair of electron while bond breaking will takes place, and it will form bond with this carbon, pi bond. And because this carbon is sharing two electrons to form the bond, this bond will break, this pi bond will break, and negative charge will be carried by the third carbon, that is terminal carbon. You can give the numbering to understand. Okay. So this effect is called as a hyperconjugation effect. If you have more alternate pi bonds, then it will undergo uh, more for shifting of these pi bonds. That is called a hyperconjugation or delocalization of these pi bonds. But because it's starting from sigma bond character, that's why it's called as hyperconjugation. Otherwise, it will become resonance effect. hyperconjugation is primarily begins with sigma character. That's why it's a hyperconjugation. Okay. So this example is already done by ma'am in class 1, 2, 3 and 4. So this is a catalyzed aldol reaction. So I hope all of you are aware of these type of examples. So when we are talking about base catalyzed, that means we are using base in our reaction. While using the base, we are carrying OH minus species. You can use any base like NOH, KOH, and LiOH, lithium hydroxide, sodium hydroxide, potassium hydroxide, or any other hydroxides, any bases. So if you have this type of species, this carries negative charge, OH minus. So because this base catalyzed reaction, so a reaction will always begins with the attack of nucleophile. Attack of nucleophile will take place and formation of enolate will be occur. So on which atom this nucleophile can attack? In a reactant or a molecule, you have to find out the electron deficient center. If you are doing a reaction with a electron rich species, this is electron rich species. So you have to find out the electron deficient center in your reactant. So as you can see here, we have here three atoms, three major atoms. Hydrogens are there. So oxygen and two carbons. So oxygen is always electron rich. It has lone pair of electrons. So this is not the electron deficient one. And this carbon is for completing the 8 electron octet rule. And attack is also not possible here. While talking about this one, this carbon is also electron deficient, and this OH minus will attack on this carbon atom. Sorry, I'm sorry for this one. So this OH minus, because it will abstract the proton. While it will abstract the proton, proton have positive charge. Correct? Proton is less electronegative compared to carbon one. So abstracting the proton from here is easier compared to this one, because this carbon is electron deficient. So it will abstract the proton from here and it will become H2O. By abstracting the proton, it will become H2O. And because this carbon will carry negative charge, then it will share here to form pi bond, and this bond breaking will take place and negative charge will generate over here. I have already explained these type of examples. So here double bond will form between this CH2 and C center, carbon center. Now again this lone pair will push. This is called enolate. This species is called enolate. Keto-enol form. All of you are aware of this one, I think. So this is enol form and this is keto form. This is keto form. So these are tautomers. Both are stable. So this lone pair will push here and a negative charge will come here. This is your keto form. So in aldol condensation, enolate first will form, because enolate are more stable compared to the keto one, enol form. Then the in second step, addition of enolate will take place to the same substrate starting material. Again the different molecule. If you are doing the reaction, there are different molecules are present. So one molecule is one molecule's proton is abstracted by OH minus, and it will attack on second molecule. So as you can see here, this carbon carrying negative charge. Here you can see, correct? If this bond breaking is taking place, it's negative charge. But in enol form, it's looking like this one. So when this lone pair will push here, here, and this will become here, here. So negative charge will generate. So this will attack on here, this carbon center. And then you have to show the correct arrow pushing, then bond breaking will take place and negative charge will generate on oxygen atom. You can see here, correct? This is a correct structure after the arrow pushing. Then after this one, protonation of alkoxide ion will take place. As you can see here, initially we have OH minus, it abstracted the proton and become H2O, correct? That means we initially we have started with negative charge, but here we have H2O. So as I told you, in starting material and product, the charge distribution should be same. So OH minus will remain as it is in product formation, so it will donate again proton. So this proton of water will be abstracted by this negative charge, negative O minus, and it will abstract proton to become a corresponding aldol condensation product with OH minus. So you can compare the starting and product. Here we have OH minus, one charge species, negative charge. Here also we have negative charge species. So the charge balance is remain same, and the arrow pushing is in a correct way, because pair of electron is moving towards oxygen atom. That's why we are showing arrow like this one. So I hope this is also clear to you. So whenever you are starting any mechanism, you have to check which is your electron rich species and which is your electron deficient species. You have to react. You have to make the reaction between these two species only. So because we have electron rich species here, that's why it's extracting proton, and means it's attacking on electrophile. This is plus H plus it will become. That's fine. Okay. Now the next example is acid catalyzed aldol condensation. Here in acid catalyzed aldol condensation, we have acidic condition. Whenever we have acidic condition, that means HCl we have. HCl means it is a H plus. H plus Cl minus. Correct? H plus and Cl minus. So in previous case we have OH minus, but here we have H plus. So H plus is a electron deficient, so it cannot attack and extract proton like the previous case. So here, because oxygen have two lone pair, now we have to we have electrophile. Correct? We have electrophile. We have to find out the nucleophile in reactant. Previously we have nucleophile, here we found out the electrophile here. Now we have electrophile, we have to search the most electronegative atom or a electron rich atom. So here oxygen is a more electron rich, so it will share the pair of electron. It can share the pair of electron to form a new bond. So it will abstract the proton. It will take the proton to form the O plus. Why we are writing plus? Because here oxygen is having three valencies. One valency, normally oxygen have two valencies, but here because it's taking proton, so it will become plus charge. It doesn't mean it's a electron deficient. So it will become OH. Correct? Formal charge. This is called formal charge. You have to maintain formal charge whenever you are dealing with a heteroatom. You should remember this one. Now, after getting this OH, what will happen? This oxygen carbon bond breaking will take place, because oxygen have three valencies, so it can this bond breaking will take place, and this chlorine will take this proton to become HCl again. This chlorine can take this proton to make the HCl, and again the double bond will form. This tautomerized form is called as enol. Enol. In previous case, we got enolate. Here we got enol. What is the difference between enolate and enol? In enolate, we are having here O minus charge, O negative. And here we have OH. It is alcohol form. OH. Here we have ion form. Ion form. Enolate. Enolate ion. Here it is enol. Okay. Then, so remember this, in base catalyzed reaction, enolate formation is taking place, and in acid catalyzed reaction, enol is forming. After formation of enol, another molecule of same acetone, sorry, acetaldehyde, again molecule of acetaldehyde will participate in the reaction. So this lone pair will push here, and this will attack on this electron deficient carbon atom. Now after formation of enol, you can say that this is a electron rich species. Correct? because if it will push electron, it can attack on any electrophile. It is a electron rich species. Then in another molecule you have to find out the electron deficient center. So in another molecule you can see here, this is a electron deficient center, so it can attack over here, right? So it will attack here, and this bond breaking will take place to form the OH. Now this intermediate will form again, because we have H plus in starting material. H we have here. So chlorine will extract this H to get make it HCl, and again you will get the aldol condensation product, and charge of reactant and charge of product will be similar, same. It will not change after the reaction. Charge should be maintained. So this is the acid catalyzed aldol condensation reaction. You try yourself first. Then if you are facing any difficulty, any doubt, we can discuss in next session also. Now, types of polar reactions. How many types of polar reactions are there? Here it is shown: addition, elimination, addition elimination, and elimination addition, and last one is substitution. So first of all, we'll talk about the addition reaction. What is addition reaction? So as name suggests, you are adding something from outside, like your starting reactant is different and you are adding some another molecule or something to the reactant. That is called addition reaction. So here you can see HBr is added to towards this alkene, and it's become addition reaction. So what will happen in this reaction? If this moiety will be treated with HBr, as I told you, H will carry the partial positive charge and bromine will carry the partial negative charge. So H plus is electron deficient. So this pi bond is electron rich and can abstract the proton. So it will abstract the proton and carbocation will generate over here. Because bromine is a electronegative atom and carrying a negative charge, so it will act as a nucleophile, and nucleophile will attack on this carbocation to form the this di-substituted product. So remember the arrow pushing here, because this is electron deficient and this alkene is electron rich, so we are showing arrow like this, and this is this arrow like this because bromine is carrying negative charge. Here bromine is nucleophile, is attacking on carbocation, that's why the arrow is showing this way. So all of you have I know all of you know why this proton is coming on that carbon atom. So this is because of Markovnikov rule. All of you are aware of Markovnikov rule, I hope. In 12th standard all of you have done anti-Markovnikov and Markovnikov rule. So here I'm not going to elaborate that Markovnikov rule. If you have doubt, difficulty, then you can ask me in next lecture. So I hope all of you got this product. Then the next one is elimination reaction. So as elimination reaction, again the name suggests, we are eliminating some atoms to get the particular or corresponding product. So here elimination is taking place, correct? So you can see here we have this reactant, and this will attack on because we have here sodium and this is negative charge. So sodium is a counter ion here, and this is nucleophile. This is our nucleophile, correct? This is our nucleophile. So it will attack on electron deficient center because it is electron rich. It is electron rich, it will attack on electron deficient center. So which center is electron deficient? So because here we have CH3, so it can take a proton. So if it will take proton, here pi bond formation will take place. this carbon will become negative charge if proton will be abstracted by this species, and then this negative charge will move like this arrow pushing, and this will knock out Br minus, correct? And this Br minus will be stabilized by this counter ion Na plus, correct? We have counter ion NaBr will form during the reaction. So now you can see from starting to end the charge distribution is same. One positive charge we have, one positive charge we have in reactant also. One negative charge, and then neutral species. So this is the way you have to show the arrow pushing. And after the elimination, because here we are eliminating HBr, H is abstracted by this species and Br is also eliminated to give the this alkene. So this is your eliminated product. This is the product of elimination reaction. So I hope all of you clear with addition and elimination reaction. Now the next type is addition elimination. So these three are homework for you. If you are not doing these things, then we can discuss in next lecture. Addition elimination example, elimination addition and substitution. Okay. So in elimination also we have different types. So you should know different type. Which type of reaction are there? We will discuss otherwise in next lecture. If you don't know, please let me know you know or no, don't know. E2, E1, E2 and E1 CB. Correct? Ma'am have explained everything in detail in her lecture. So please go and watch her lecture on which is available on YouTube. If you are not getting anything, you can ask me in next live session. Correct? In substitution also SN1, SN2, SN1CB. Correct? Through conjugate base. So please go and watch lecture and give the one example of each and every type of reaction. Now I have taken some questions. So from previous years or more than that old assignments, you have to give me the correct answer. So the first question is, the correct order of stability of the given radical is. What is the stability of radical? Carbocation or carbanion, all of you are aware of it or not? See here, primary from primary to secondary is, sorry, I will draw here first carbon anion, carboanion. This is a primary carbon, correct? It is more stable compared to the secondary carbon. Bond. And tertiary carbon ion is least stable. Least stable. Okay. This is the stability order of carbon ion. While talking about the carbocation, CH3, sorry, here I have shown the, okay, yeah, is least stable compared to the this one. The trend is different, opposite exactly. So always remember this trend, then it will become easy to understand the stability of carbocation and carbon ion, and it will help you to do the rearrangement reactions problems also. Okay. So the tertiary carbocation is more stable compared to the primary one, while the tertiary carbon anion is least stable, and this one is more stable. Same pattern like from carbocation is followed by radical also. The tertiary radical is more stable compared to the primary radical. Okay. So here we have to find out the most stable radical. So remember here we have here secondary radical, here primary and here primary, right? But one more thing is here. This radical have conjugation with this pi bond, and this pi bond is have in conjugation with all these other two pi bonds. So this is in uh, extended conjugation. This is called extended conjugation. So this radical is stabilized by this phenyl ring because it has three pi bonds. So this radical is become stable because of the presence of pi bond, and because here three pi bonds is there, that means it is the most stable one. Now in this case, because radical are electron deficient species and electron pi bond are electron rich, so it will stabilize this radical. Same here also, this radical is stabilized by this pi bond, this pi bond. That's why this is also a stable radical. And here you can see both are primary carbons. So that's why, because this radical don't have any stabilizing pi bond, that's why this is least stable in this case. So the most stable carbon radical is third one. So which example have third one? Sorry, first one. Sorry, this one, first one, this one, correct? Second and fourth are having first as one as a most stable carbon radical. Then the second stability of carbon radical is this one because of presence of this pi bond. That means the second one is the second stable carbon radical. So first, then second, then third one is the least stable. So this is the correct option. Any doubt, any difficulty is there? You can ask me. Okay. Now the next question is here. The most accurate arrow pushing mechanism for the given reaction is. So you have to find out the most accurate arrow pushing mechanism. Anyone? Please feel free to answer. So as I told you, you have to check the both reactant. Here we have this reactant and acetone, and this is our nucleophile or another reactant. So in both the reactant, which one is electron rich? So you can see here we have lone pair of electron present on nitrogen atom, correct? So that means it will act as a nucleophile. So nucleophile means it have lone pair of electron, means electron rich species, not always electrophile, but nucleophile electron rich species. So it can abstract proton, correct? So it can abstract the proton. Yeah. Mhm. It can abstract the proton, and then this OH manus will attack on this electron deficient carbon, and then oxygen will carry negative charge. So if you will see closely, all of them are showing the same thing except fourth one. So this one is eliminated. Correct? Now here in first example you can see that lone pair of nitrogen is abstracting the proton, and here arrow pushing is showing from oxygen atom to here. It's not clear that this bond breaking is taking place or not. So this is not the correct way to show the mechanism. You have to show the bond breaking also. You cannot show directly this way. In this example you can see it's abstracting proton, then this bond is directly attacking on this carbon deficient center, which is also incorrect, because all of you know that OH minus is attacking. That means this bond should move this way and this should attack over here. You can see in second option, this is abstracting proton, arrow pushing is moving here, and then oxygen negative charge will attack over here and will moving towards this direction. So this is the correct way to show the arrow pushing mechanism. All of you are clear? Please go and watch ma'am's lecture, then this will become very clear to you. The next question is the correct resonating structures of the most stable enolate form of the given compound. So this is the given compound. You have to find out the most stable enolate resonating structure. Which one is stable one? Most correct. So here you can see that in first option we have, first of all you have to check the pi bonds. We have two pi bonds. Okay. Then here we have negative charge on oxygen. Correct? And pi bond is moving towards this way to get the resonating structure, this one. So first you should eliminate the wrong answer. Anyone? See here, if this oxygen, this pi bond will move towards this direction, so you will get this one. But here you can see here, this is not in conjugation with this double bond compared to the other structure. You have to compare here structure, because they have asked for the most stable one. Not this is also a resonating structure, but this is not stable as much as stable compared to the other structure. So this is ruled out. Okay. Now the other examples, here only the proton abstraction is showing here, negative charge. So this is also not this is in conjugation, but not correct as other structures. So here you can see this is in conjugation, negative charge. This can go here, and this will this double bond will move here. This will move here, and this will move here. So this is the correct delocalization of pi bond. So this is the most stable resonating structure of this molecule. Any other structure is there? Yes. If we will moving the arrow, we are getting this one also. Correct? And this is also stable, because here also delocalization is possible. This pi bond can delocalize here to get this structure, to give this structure, sorry, and this will give this structure after delocalization. So these three are stable form of resonating structure. Correct? I hope all of you got it. Next question. The reaction mechanism for the reaction below can be classified as As I told you, I have given you homework for addition, elimination, elimination, addition, substitution reaction. So this is also homework for you. You have to find out which reaction type this one is. We will discuss in next session in detail which type of reaction is this. Okay, all of you got it? I will give one hint here. This mechanism is going through the benzyne intermediate. Benzyne intermediate. Okay, this is a hint for you. You have to find out the correct answer for this one. So I hope all of you got today's lecture, and here's the lecture's end. Now I will give the revision. Short revision. So in today's session we have discussed the introduction of reaction mechanism. So as I told you, reaction mechanism is a pathway of the reaction to follow to get the particular product. So it is a pathway of the reaction. And then we have discussed the type of reaction. So there are three types of reaction: polar mechanism, radical mechanism, pericyclic reaction. So in polar mechanism we have discussed the electrophile and nucleophiles. In radical mechanism we did not have discussed deeply in this lecture, but it is a equal distribution of electrons between the two atoms or molecules. And then pericyclic reaction we didn't have discussed here, but it is a follow by the concerted process. The reaction is follow the concerted process. That means the bond breaking and bond making is taking place at same time in a single step. Then we have discussed polar reactions in detail. So as we have discussed four different effects of polar reactions, four different factors which affect the polar reactions. The first was electronegativity or inductive effect. So electronegativity we have seen here from left to right. Electronegativity is increases, from top to bottom it decreases. Uh, and we have discussed the electronegativity of oxygen, carbon, nitrogen, fluorine. So here I have told you fluorine is the most electronegative atom in a periodic table, and followed by the oxygen and other halogen atom. Then we have discussed the resonance effect. Resonance effect is nothing but the interaction between the lone pair and pi bond or of two pi bonds. So this is a delocalization of pi electrons is taking place in resonance structure. This is also called as mesomeric effect. Sorry, this is also called as mesomeric effect. Which is also denoted by plus m, correct? Then we have discussed how we can show the arrow pushing. So we have discussed the four different rules. First rule was the curved arrow should be used, and with double-sided overhead arrowhead. That means two electron transfer is taking place. And when we are showing the single-headed arrowhead, that means a single electron transfer is taking place, which is this single-headed arrow is also known as fish hook arrow. Then in rule number 2 we have seen that electron flow should be always from electron rich species to electron poor species, that is from nucleophile to electrophile. Then we have discussed the rule number 4, that is the overall charge in during the reaction stays the same, that is the same charge of product and reactant should be there. The charge on reactant species should be same as the charge on product species. And the fifth rule we have followed the atoms of the product should match with the reactant. And we have done the different examples. Then we have solved different problems. You please go through these problems. And if you are finding difficulties or not getting anything, you can ask me in next live session. Then here also we have discussed the resonance form of these structures, and we have discussed one more thing. If we have two pi bonds in our starting moiety, then it should be carry carrying the same pi, pi electrons throughout the structure. So here we have two pi bonds, here we have uh, two pi bonds, here triple bond we have. That means one is sigma bond, two are pi bonds. So pi bonds are same here. Again we have to see here octet rule is not followed by carbon. That's why this is not the correct resonance structure. So, so you have to keep these things in mind to check the correct resonance structure. Then we have done some different problems like arrow pushings this way, and we have write down the different possible resonance structure. Then we have discussed the hyperconjugation effect. As you can see, hyperconjugation effect is because of the sigma character. That's why it's called hyperconjugation. It's similar type of effect like resonance effect. Then we have done the base catalyzed aldol condensation reaction, and we have discussed the acid catalyzed aldol condensation reaction. Both mechanisms are different, but the final products are same. The base catalyzed reaction was moving through the enolate ion formation, and the acid catalyzed reaction is carried out with the enol formation reaction. Enol formation. Then we have discussed the types of polar reaction. Here we have discussed addition, elimination reaction, addition, elimination, elimination, addition, and substitution reaction are also there on YouTube, which is discussed by ma'am. This is homework for you today. Then we have done few questions. Here stability, we have discussed the stability of carbocation, carboanion, and radical. So here we can see carbon anion is following the exactly different trend from the carbocation. So primary carbon anion is most stable, whereas the primary carbocation is least stable, and tertiary carbocation is most stable. Correct? And similar criteria is followed by the radical also. So primary radical is least stable, tertiary radical is most stable. Radical is always follow the carbocation pathway. Carbocation pathway. But here in this case we have observed that because here we adjacent pi bond is present here, so that's why this radical is stabilized by delocalization of these pi bonds, presence of these pi bonds. And here also because of the presence of this pi bond is this radical is stabilized. This pi bond is stabilizing the radical, that's why it is also a stable radical. Whereas here we can see, here we don't have any pi bond, so this is the least stable radical compared to these two radicals. So that's why the trend will be first, second, third, like this way, because here we have three pi bonds. Then next we have discussed the accurate arrow pushing. As I told you, arrow pushing should be very clear because we have here nucleophile nitrogen here. Nitrogen lone pair will abstract the proton. Because it's abstracting the proton, this bond will break, and this bond should move here, and then this oxygen will attack on this carbocation. So arrow pushing should be done clearly. Here this arrow is missing, that's why this is not the correct answer. Whereas here also it's showing this bond is attacking on this carbon atom, which is also incorrect. And here the trend is totally different. This one is attacking here, and this is not the correct mechanism, so it is ruled out first only. So the correct mechanism was this one we have discussed. Now here we have discussed the correct most stable resonating structure. However, this one is also correct one, but this is not the most stable one because here conjugation is missing. That's why, and here because conjugation is not disturbing these three cases, that's why these three options are correct options, which is also called as a most stable enolate form. Then this question was homework for all of you. So please try to do by yourself. If you are getting difficulty, then we can discuss in next session. Thank you. Thank you all of you for your kind attention. Yeah, yeah, yeah. Yes. Sorry. Yeah, yeah, sure.